for your keys only. This project is mainly to generate AES keys using ANNs and prevent sharing of those AES keys on the network. While using the same ANN, we can regenerate the AES key using which the data is encrypted. So the advantage is dynamic AES key generation and tightly coupling the timestamp of the message that is encrypted, because timestamp also participates in the AES key generation, and data encrypted with that AES key can be decrypted provided it's on the same timestamp, and the timestamp, if it is beyond certain range, the server would not accept it to prevent replay attacks. And the AES keys produced by ANNs are hard to guess, that is, from the inputs that are supplied it is not possible to guess the AES keys, and the same ANNs are replicated on the server side and the client side in order to secure the communication. So as depicted in the picture, the client first generates a random string, which is a UUID and a UTC timestamp of the machine, assuming that the server is also having the same UTC timestamp. The ANN feeds the random string in the UTC timestamp to get the AES key depicted in red color. Then it uses AES, Advanced Encryption Scheme, to encrypt the message, and that message is sent on the network along with the inputs that are given to the network, which are random string and the UTC time. Only using the inputs and the same ANN, the server can regenerate the AES key, decrypt the message, and process the request. So the advantage here is the AES key by itself is not shared on the network, and the inputs that are required to generate the AES key are traveling on the network, and the inputs have got no correlation with the AES key. So it is hard to guess what is the AES key that is used to encrypt the data that is going between the client and the server, and the client can keep on generating new AES keys and encrypt the data, and the dynamic nature of it is the advantage of this research. The aims and objects of the research are to secure communication using ANNs. The objectives of this research are to deliver the ANN securely from the client to the server, from the server to the client, because ANN has its weights and biases, which are the secret ingredient to generate the AES key. We don't want the ANN to be public, because if anybody with the same ANN, they would be in a position to generate the same AES keys. So ANNs would be encrypted and delivered back to the client. The client should be the only one that would be in a position to decrypt the ANN. And non-repeatability and non-conflict of AES keys, that is, two ANNs should not produce the same keys. The same ANN, when tried with multiple inputs, should generate non-conflicting or non-repeating AES keys, and no correlation between inputs and outputs of the ANN, and replay attack prevention, and non-feasibility of a learner ANN model. If at all there is a learner ANN which knows all the inputs and the outputs emerging from an ANN, it will never be able to converge onto the AES keys, because it will always be a poor approximation of the ANN. It will not be in a position to generate the exact AES key. So if you go back to the literature review, over last 2 decades, a lot of research was done in the combination of ANNs and AES keys, and AES keys with various algorithms, and multimedia with AES keys, and multimedia with a lot of cipher key generation. So in the first image, we can see that encryption ANN was used for both encryption and decryption with a limited data set. So that is, on a trained data set of plain text and cipher keys, ANNs were trained to generate the cipher keys produced by AES encryption. Likewise, another ANN was trained, the converse of it. It will take the encrypted data and produce the plain text, but this is a very limited data set which is not applicable to today's world. And the second type of ANNs are ANNs in combination with AES encryption. That means the last layer or the module output of ANN would be converted or encrypted and would be used. And similarly, at the decryption side, the data that is encrypted would be decrypted and would be fed back into the ANN model to produce back the original data. So this is the two kinds of researches that were used to secure the outputs of the ANN, which are supposed to be shared on the network. And third type of communication is generation of cipher keys is take multimedia messages, use some algorithm, and generate cipher keys. But the problem with this approach is, if the algorithm is known by the attacker can fetch the same image, and unfortunately public images were used to generate cipher keys, and if the image is known by the attacker and the algorithm is known, the cipher key generation can also be done. That means there is no more secrecy left in the solution. And the literature review also includes mutual synchronization, where as depicted in the first image, there are two clients which start with two random models with the same architecture, and eventually they converge by exchanging the errors. That means they give some sample inputs and outputs, and based on the errors they both converge on the weights online through mutual training or online synchronization, which is known as mutual synchronization. But this approach requires more number of iterations between two clients in order to realize the same ANNs. There is no sharing of ANN on the network, but the thing is, the ANNs by themselves they have to be trained online, which is a costly thing, and it is non-deterministic also. It takes multiple iterations for them to converge. Another type of research is mainly in the medical area, where sensitive images are encrypted, and ANNs are made to train on encrypted images. That is, they don't train on the actual images, they do categorization on encrypted images. So somehow they are able to understand the patterns in the encryptions, and they are able to work with encrypted data, and the data by itself is very sensitive, like a human patient data or organs data or brain scans or whatever. But for the ease of reflection, in this picture I have used animal categorization. That means ANN is basically doing categorization with encrypted data. However, this is kind of a limited research. Actually no encryption and decryption is happening here, but only dealing with encrypted data. In this methodology, we use ANNs to produce AES keys. So the methodology employs two types of models. One is the simple ANN and the complex ANN. Both differ by only in terms of layers and the architecture. Otherwise, the inputs and the outputs are the same. That is 256 bits inputs, that is combination of ones and zeros of 256, and the outputs that emerge out of them are 256 floating point vectors. That is, the output is a 256 bit array of floating point values, which will get converted into a AES key. And once the model is generated with random normal distribution and tanh activation functions. Why tanh? Because we want to clip the outputs of each layer between +1 and -1. This is needed for us to convert easily the outputs into AES key bits. And once the model is created, a quick training is employed, where quick training is basically generate random inputs to a model and train it so that apart from the random normal weights, there is further normalization of weights. So quick training plays an essential role of varying the weights apart from the random normalization that was done during the weight initialization and the tanh. So it adds to the randomization. And how the inputs are fed into the ANN is depicted in this combine and feed module. In combine and feed module, we take MD5 hashes of the random string and the UTC timestamp, interleave them in an alternative fashion, their bits which are zeros and ones, interleave them in an alternative way so that we add further randomization, and this alternative interleaved combination is fed into the ANN as 256 bit inputs, 128 from the first random strings MD5 and 128 from the UTC timestamps MD5. And the output that emerges is seen in the picture at the graph below, which is the green output, which is a random ANN output which consists of floating point values. We calculate the mean of those values, and all the values that lie above the mean value are treated as ones, and the ones which are equal to or below the mean assume the value of 0. That way we are generating a 256 bit key, AES key, which is fit to be used for data encryption. And there might be some errors around the mean calculation, which we'll see as a part of our result. And the third picture shows the methodology used overall. Two random inputs are combined and fed into the ANN to produce a random output, and they are converted into an AES key which will be used for data encryption. So the client and server, in order to start the ANN based communication, first they need to ensure that the ANN itself is communicated securely, generated at the server side and communicated securely from the server to the client. For that, the client uses RSA encryption. It generates a public private key pairs, and it gives out the public key and says the server to generate an ANN model, the H5 file, and encrypt it using that public key. But the server, what it does is it generates another AES random key, and it encrypts the model using that random key, and it encrypts the AES key using the public key of the client. so that the decryption will be easier. Using AES encryption will be faster, especially with ECB and 0 byte padding modes, so that the encryption part of the model will be easier. The model itself is a huge file, and we don't want to do RSA encryption directly on the model. So the server generates a random AES key and encrypts the model with it, and it encrypts the AES key using the public key given by the client. The client uses the private key to decrypt the AES key, random AES key with which the model is encrypted, and it will do AES decryption to arrive at the ANN model, and which it will load it into the memory using KRS, and it will use that model further on to secure communication. So as depicted in this picture, the ANN will be employed to do secure communication. It takes the random input and the UTC timestamp, generates an AES key, encrypts the data. When sending to the server, it sends the ciphertext. Along with the ciphertext, it gives out X1 and X2, which are random inputs that are required to generate the AES key, and the ANN model ID, which was used by the client to generate the AES key. The server, upon receipt of the request, it would first load the ANN, which the client claims that it has used to generate the AES key. It will replay the inputs fed by the client into its own model, and it will generate the same AES key, and it will decrypt the message, and it will process the request. So the AES key that is generated at the server side will be the same AES key that the client has generated without transmitting that AES key excuse me, onto the server side. So this means that the AES key by itself is protected, and the mechanisms to generate it are shared. So this is the way in which the solution secures the communication between the client and the server. And to mitigate replay attacks, we already have UTC timestamp as one of the inputs given to the ANN. So if a client uses a wrong timestamp, the server is going to reject it. If a client is going to take an old message and going to change the timestamp, the server will not be able to decrypt the message and reject it. So either case, the replay scenario will be honored, because an attacker, if without knowing value of the payload, if he is able to replay the same payload on the server and the server is able to honor the request, that's a problem, because the request can be anything like resource creation or resource consumption on the server, and we don't want DDoS attacks happening on the server. So this solution also incorporates replay attack, which is a very important security tightening that is needed to make the modern world communication resilient to replay attacks. So this research work includes replay attacks along with secure communication. And these are the results. So the client and server, the server was coded in Python Flask application as a Python Flask application, and it was able to serve 3 clients: the Python client, the Java client, and the JavaScript client. The Python and the Java clients were able to generate their own RSA public key pairs and could get back a secure model, an encrypted model H5 from the server as discussed, and they were able to use that model, load it, and use it for further secure communication. Even replay attack scenario is also handled. But for JavaScript client, TensorFlow.js, which is the library required to load ANN model into the JavaScript on the browser, it is incapable of dealing with encrypted models directly. So the only recommendation we have is either to use HTTPS or to do decryption using intercepting of XML HTTP request of the JavaScript client, which is the future scope of work. In this work, we just depict loading of TensorFlow.js model and secure communication, which was successful, and even replace scenarios were addressed. So coming to the correlation, there is a very weak correlation between the inputs and the output bits, which are AES key bits after conversion of raw ANN output values. So the simple ANN has got a range of -0.2 to +0.24, and most of the values centering around 0, a normal distribution centering around 0, and the complex ANN after 1 lakh iterations is able to on a 10,000 sample is able to have a correlation of -0.8 to +0.17, which is even weaker correlation because it has more layers to compute the final outputs. So complex ANN is able to have a weaker correlation than simple ANN, but simple ANN is also centering around 0. Both are centering around 0, which is a good thing, because it means that the ANN keys by themselves are hard to be guessed from the inputs alone, because inputs travel freely on the network. We want to ensure that the AES keys that they are used to generate are having no correlation. Out of 1 lakh iterations, both simple and complex ANN with and without quick training did never had any repetition of AES keys, which is a good thing, because AES keys when they repeat, there might be a chance that they will repeat further. So with varied inputs, the AES keys were not repeating. Also, the collision between two models was not there. That means if two models were taken, simple or complex ANNs, up to 1 lakh iterations were tried, and there were no collision of AES keys. That means both generated different AES keys, and in any instance with the same inputs, the two models did not generate the same AES key, which is a requirement for us to have two models generate varied AES keys. So clients using two different models will be assured of generating different AES keys, not clashing with one another. Model sizes were also estimated. Simple ANN takes up to 1 MB, sometimes more than 1 MB, and complex ANN takes 120 MB. The same TensorFlow JS variants, which is a directory containing model JSON and shard files of weights and biases. The simple ANN takes just 3 KB, the model JSON, and the shard files of one shard file of 80 KB, which is a very less space. And complex ANN, the model takes around 12 KB, and weights and biases occupy maximum memory of 4 MB each, 15 or 16 such files. So complex ANN in general holds more memory, but it is produces more weaker correlation than simple ANN. Simple ANN though acts like a very good optimized memory, and it can be used, it can be rotated frequently and used instead of a complex ANN. And the learner ANN is also not able to learn effectively from a subject ANN. The MSE drops, that means the floating point values that the learner ANN is coming close, but the learner's ANN's AES keys L2 norm with the subject ANN's AES key is reducing, but it is not touching 0. The total number of different bits between the learner ANN's AES keys and the subject ANN's AES keys is also reducing, but they are not touching 0. And learner's ANN's accuracy is at max going up to 70%, which means that the learner ANN is not good enough. Even with 1 lakh iterations of training, it is not good enough, and it's a poor approximation of the real ANN. And also an experiment was conducted that how many different weights between two models can generate non-repeating keys. Initially, two models were taken with same weights, and iteratively the number of weights they have, with the number of different weights they have, slowly are grown. So initially there was only one weight, and eventually we are taking the experiment up to 50 different weights. So if you see the graph, even at 50 different weights, the repetition of keys is greatly reducing, and their L2 norm is also increasing. That means the models are already diverging. With a model having 15 lakh keys, as small as 50 different weights are producing varied set of AES keys, which is a good thing, which encourages a large client base on the model. That means servers can produce randomized models varied with different weights, and they can achieve the goal of having non-conflicting keys with the clients. And the error rate, models were generated on Google Colab on TPU, and the same model was executed on the local machine with 50,000 sample inputs and outputs. They were tested. So out of 50,000 samples, only 2 AES keys did not match for simple ANN, and 10 AES keys did not match for complex ANN. The error percentage is very less, 0.004% for simple ANN and 0.02% for complex ANN, which is very less. And also the Levenshtein distance between the differences was 1. That means only 1 bit out of 256 bits were different. As depicted in the example, Google Colab TPU was generating B, and the local machine was generating 9, and the binary representation of it shows that the third bit was assumed as 1 by Google Colab TPU and assumed as 0 on the local machine. This is because of the value being very close to the mean value. So any better metric can be employed in future, or a margin of threshold where in that margin ones and zeros can be treated as fuzzy. That is, both they can be tried for both 1 and 0. That is the remediation. So conclusions is secure communication is achieved between client and server, and applicable to different clients. JavaScript client and Python client were tested. Secure delivery of model was tested for Java client and Python client. For JS client, we recommend HTTPS for now because we don't have a direct encryption mechanism. And error rate of key mismatch was also very less between different machines that were generating the models. And remediation process was also given, like generate a new AES key and transmit in case of AES key mismatch, or in case of encryption failure on the other side. That means in case of failure, you can retry generating a new key and send it. And a margin can also be put, as discussed, around the mean value, so that those bits can be treated as fuzzy. And future work is more randomization, more different types of architectures, and better metric than mean value. And secure delivery of ANN with JS client can be assumed as a future scope of work. And pre-generation of ANN models to avoid bandwidth issues on the server. And mobile applications can be pre-fed with an ANN to do secure communication rather than getting it online over the network. And the same approach can be used for document encryption. That is, ANNs can be used to generate AES key with which documents can be encrypted and shared. And ANNs as a protocol layer, like just like TLS layer today, it uses symmetric keys to generate and transmit them securely to the other side. The same work can be done by ANNs. That is, ANNs can be employed to generate AES keys. So this is the overall conclusion of the research. It has been implemented completely, and it's a working solution. And all the GitHub repository links are given here, along with the Python notebook implementation, which covers entire concepts which are discussed in the research. And Java client, the Python client, and sample outputs are also discussed in the GitHub repository. Thank you.